Welcome all of you. In the last class, I gave general introduction to nuclear spin and how to arrive at the nuclear spin based on the simple empirical formula depending upon atomic mass and atomic number of different elements and different nuclear spins. And I also discussed about two important quantum number, spin quantum number I and magnetic quantum number M. And I said they are related to each other, they are quantized. And I also discussed for M is equal to M depends upon I, for particular value of M we have different quantization directions which takes the value from minus I to plus I in steps of 1. For example, for spin half nuclei we have two possible orientations, minus half and plus half, and we also worked out what is the magnitude of this quantization direction, what is this magnitude of spin angular momentum, that also we worked out. And I said there is a magnetic moment mu because we can treat spin of nuclei as a tiny magnet. This magnetic moment mu depends upon, it is dependent on what is called gyromagnetic ratio of the given nucleus, which is constant for a given nucleus, which is different for different nuclei. And I said even though proton and carbon have same I and same M, I is equal to half, M equal to minus half and plus half, but their gammas are different because it depends upon mass. As a consequence, magnetic moment mu is different. Since mu is different, we can study independently, individually these two can be studied. So that is what I said, for any element of the periodic table if you look at it, gamma is different. As a consequence, every element of the periodic table, so long as it possesses a spin, can be individually studied by NMR. This is what I discussed last time. Now we will go further today and I will introduce about what is called Zeeman interaction. What is a Zeeman interaction? What is the basic requirement of NMR is interaction of the magnetic moment mu with the static external magnetic field. External magnetic field is a huge magnetic field which is static and denoted as B naught. The magnetic moment mu of the nucleus should interact with this. So nuclear spin quantum number I, that must be non-zero, that is what I said. I told you mu depends upon this I, and if I is equal to 0, I worked out and showed you in the last class mu is 0. Since mu is 0, there is no NMR. That means I must be present to detect NMR. That is the reason why for the nucleus which is spin 0, there is no NMR. That is what we discussed. And this is what I showed you last time, and also again I am writing mu is equal to gamma into h cross I into I plus 1, and interaction of mu with the B naught if you consider nuclear spins. As soon as you put this nuclear spin, put it inside an external static magnetic field, what is going to happen? The nuclear spins start aligning with the static magnetic field. Initially they are all randomly oriented, there is no preferred orientation direction of the nuclear spins. As soon as you put them in the external magnetic field, they start aligning with the static magnetic field. How do they align? Some of them align in the direction of the field, some of them align in the direction opposite to that of the field. These are the preferred orientation directions, and the energies of interactions for both these orientations are different. If the spins are aligned in this direction, it has one type of energy. If the spins are aligned in the direction opposite to the magnetic field, it is a different energy, and these two energies are different. And in fact we can calculate these two energies, and in the absence of the magnetic field, these two energies states are not separated, they are all degenerate state, okay, in the absence of the magnetic field. As soon as you put it in the magnetic field, then there is a removal of degeneracy. The energy levels get separated out for both spin half or orientation direction in the direction of the field and the orientation in the direction opposite to that of the field. Both get separated out, okay. And conventionally, and you can also understand from Boltzmann distribution, more spins are aligned in the direction of the magnetic field. than opposing it. This is a Boltzmann requirement, it is a Boltzmann distribution. This is what is going to happen, and this method of this way of separation of the two energy states, or what is called removal of degeneracy by the interaction of the magnetic movements with the external magnetic field, is called Zeeman effect. It is a Zeeman effect. Now, for spin half nuclei, we can work out by simple mathematics. E equal to minus mu dot B naught. Mu is the magnetic moment and B naught is the static magnetic field. In the absence of the magnetic field, when B naught is equal to 0, you can see all the spins are oriented. There is no preferred orientation, both orientation in the direction of the field, up and down, both the spin states are not separated, they are degenerate state. You can't separate them out here in the absence of the magnetic field when B naught is equal to 0. Now, as soon as I put it in the magnetic field, which is non-zero, then what is going to happen is there is a separation of the energy states. One corresponds to minus half, other correspond to plus half. This is for the anti-parallel orientation, this is the parallel orientation. This is orientation in the direction of the field, this is orientation in the direction opposite to that of the field. And when there is a separation of the energy, you can find out what is the energy difference. When the energy states are separated, you can find out what is delta E. And you all know, once it is this thing, as I told you, there are more spins in the direction of the field than in the direction opposite to the field. There is a small excess population of the nuclear spins in the state alpha is equal to plus half, and this is called a removal of degeneracy. Now, energy of interaction of the magnetic moment with the magnetic field we can calculate. How do we do that? E equal to minus mu dot B naught, that is an equation, general equation written. You may ask me a question, why did I write negative? E is anyway always energy is positive, but it is to ensure that the spins oriented in the direction of the external magnetic field has lower energy. That is a assumption. That is the reason why deliberately E has been put, negative sign has been put for this. So, interaction energy is given by mu dot B naught, both are vectors, it is a dot product of the vectors. Okay, this is the energy of interaction of the magnetic moment. For two different spin states, E equal to plus half and minus half, that is E equal to alpha and E equal to E alpha and E beta, we can work out the energy is like this. One is minus half gamma h bz over 2 pi, other is plus half gamma bz over 2 pi, h bz over 2 pi. Notice the energy of the beta state here is more than the alpha state. Of course, you know why, because E equal to minus mu dot B naught I told you. So, since it is minus is there, beta state is minus half, minus half into minus half is plus half. As a consequence, always we see that as soon as you put it in the magnetic field, this is the higher energy state, m equal to minus half, this m equal to plus half is the lower energy state. This is what is going to happen. So, as soon as you put this spins in the magnetic field. So, this is the energy separation, this is the energy of each of these two spin states, E alpha and E beta. When I calculate the energy bit of each of these two states, I can calculate the difference in the energy, delta E. Simple equation from the previous equations you can calculate. Of course, you all know energy separation is related to frequency h nu. Equate these two now. Then what will happen? When equating these two and do some simple jugglery, you will find out nu is equal to gamma into B naught over 2 pi. This is an important equation of NMR called the resonance condition, where nu is equal to gamma, B naught and 2 into pi. This is the resonance condition. This basic equation is the one which is responsible for seeing NMR signal, and this is the equation which has given 4 Nobel Prizes in NMR. Simple equation, so many interactions were there, and the research carried out in this NMR spectroscopy based only because of this equation, basic equation, resonance condition. 4 Nobel Prizes were obtained. So, this is what is the basic resonance equation, and as you can see here, nu is a constant for a given nucleus, I told you, 2 is a constant, pi is a constant, and of course, magnetic field you can keep yourself constant, there is no need to vary it. That means frequency is constant. Now, I will double the magnetic field. what will happen? This will get doubled because other 3 parameters remain same. That means the resonance frequencies vary linearly with the magnetic field. If I have a magnet and I get the resonating frequency for a given nucleus, I calculate for a particular spin for a, like proton or carbon, nitrogen, whatever it is, and I double the magnetic field, simply the resonating frequency I have to double it. That is what happens. Resonance frequency gets doubled by linearly changing the magnetic field. And this is what happens. The energy level gets separated out because the frequency doubled. Frequency is related to energy separation. As a consequence, when I double the magnetic field, the energy difference, energy state difference also gets doubled. This is what happens. For example, at a given magnetic field, 4.7 Tesla. Okay, this is alpha state and the beta state. I calculate the energy difference and let us say this is the 200 megahertz I calculate. I simply double the magnetic field, go to 9.4 Tesla. See what is going to happen now. The delta E is equal to 400 megahertz now. Just doubling the magnetic field 4.7 to 9.4, the energy separation became double and the resonating frequency also doubled. There are few advantages of this. As we go ahead, I will tell you. When you increase the magnetic field, you have increased sensitivity and you also have increased resolution. So, when you are doing the NMR peaks, if you are seeing the NMR resonance at higher and higher magnetic field, there are certain advantages of sensitivity and resolution. As we go ahead further, we will discuss these things. This is a simple table which tells you. Look at in this column we have a magnetic field put here, in this column resonating frequency. Look at it at 100 megahertz, the resonating frequency magnetic field is 2.3487 Tesla. Remember, magnetic field is always expressed in Tesla. 1 Tesla means 10,000 Gauss. Strong magnetic field, very strong magnetic field. Now I double the magnetic field, 2.3 become 4.6, already you go to 200 megahertz. In fact, what I am going to do is I am going to increase it 8 times, 2.34 I make it 18.78, you see the magnetic resonating frequency became 8 times larger. This is basically what is going to happen. So, resonating frequency varies linearly with the external magnetic field. Okay, with this I want to tell you one thing. Where does NMR spectroscopy appear in the electromagnetic spectrum? Remember, in the very first slide I showed you, in the electromagnetic spectrum, I said NMR spectroscopy appears in the radio frequency region. Correct. Let us understand this, whether it is true or not. We will calculate ourselves. I know the resonating equation, resonating condition. I know all the other parameters gamma, 2 and pi. I will fix the magnetic field as 2.35 Tesla. And I know what is the gamma value for proton. It is 26 point something into 10 to the power 7 radians per Tesla per second. I plug in all these values to this equation and then calculate what is the resonating frequency. It turns out to be 100 megahertz, which is the radio frequency region. Okay. Now I will double the magnetic, I will increase the magnetic field to a large value. I go to 14.1 Tesla, plug in this value, all other parameters remain same. I am not changing it. If I plug in the value for all of them and work out, you will see the resonating frequency is now 600. For a given magnetic field of 2 point something, it was 100 megahertz. Now when it is 14.1 Tesla, it is 600 megahertz. Okay. What about carbon in this magnetic field? Where does carbon resonate? I know proton resonates in 2 different magnetic field at 100 megahertz and 600 megahertz. I calculated. Where does carbon come? Put the value of carbon gamma, that is 6.725. All other parameters remain same, only gamma is different. I plug in those values and calculate at 100 megahertz of the proton, where the magnetic field is this one. Okay, a very small value of magnetic field. Now I am going to 2.35 Tesla magnetic field. The resonating frequency is 25.15 megahertz. Remember, for this magnetic field, proton was resonating at 100 megahertz. Gamma of carbon is 4 times smaller. As a consequence, the resonating frequency of the carbon is 4 times smaller. Same thing. Now go to the higher magnetic field where we calculated for proton, that was we got 600 megahertz, but now same thing for this, if you plug in the value of gamma for carbon, it turns out to be 150 megahertz. So that shows for all these nuclei, with two examples which I took, NMR is coming in megahertz frequency range, which is in the radio frequency region. That is why NMR comes in the radio frequency region, because radio frequency region it goes from small few megahertz to few 1 or 2 gigahertz. As a consequence, we are going to observe NMR in the radio frequency region. Now let us do reverse engineering. Let us say I have protons in a given molecule which is in a given magnetic field resonating at 300 megahertz. Now if I ask you what is its magnetic field strength, of course we can calculate it. What we will do is plug in this value. Earlier you plugged in value for B naught and calculated what is resonating frequency. Now I know resonating frequency, I have to calculate B naught, rearrange this equation. Now plug in the values for 2 pi nu, what is the resonating frequency 300 megahertz. I know the value of gamma, calculate it. For example, for a certain value for this 300 megahertz, B naught turns out to be 7.04 Tesla. See, we know how to calculate the magnetic field strength when I know the resonating frequency of a particular nucleus. I can calculate at what magnetic field the experiment was done. Or in other words, if you tell me what is the magnetic field strength you have, I can tell you different nuclei will resonate at which frequency, what are the frequencies at which different nuclei will resonate. That is what I can detect, I can calculate. Okay. So what is the radio frequency range? It goes from 20 kilohertz to several gigahertz. Where did we calculate the resonating frequency of proton and carbon for different magnetic fields? They were all in megahertz. As a consequence, I am telling you NMR is detected in the radio frequency region. This is what I said in the very first slide when I showed the slide where electromagnetic spectrum was shown, and I asked you a question, where does NMR comes, and I said it is RF region, and this is what it is. We can confirm it because now we know the resonating condition, we know gamma, we know B naught, we can plug in the values and get the resonating frequency, and these are all in the radio frequency region. Okay. Now if you look at it, if you go to any NMR laboratory, you will see big cylinders like this. Okay, big cylinders like this. What do these things? If you see, look at it, there are some numbers written here, 400, 700, 600, all those things. What do this mean? 900 here. What do this refers to? This is the resonating frequency of protons. These cylindrical materials, what you see in any NMR lab, there are huge magnets, strong magnets. And if I say 400 here, that means in this magnetic field, proton is resonating at 400 megahertz. In this magnetic field, proton is resonating at 900 megahertz. This is what is understandable. You have to go and see in different NMR spectral laboratories. If you go, if you see different cylinders like this with a number written, that is the spectrometer frequency at which protons are detected in a given magnetic field. This is the magnetic field, and you should know the strength of this because you know what is the resonating frequency. That is what it is. And highest magnetic field currently available for doing NMR is 28.2 Tesla, which is huge, close to $20 million, very, very huge. But only hardly some 3 or 4 such spectrometers are available in the world. It is very difficult to afford and also to purchase these things. So hardly some 3-4 laboratories are there. Just to give you an idea, present day world we can go up to 28 point Tesla magnetic field, where we can get the resonating frequency of protons at 1.2 gigahertz. Huge magnetic field, and resonating frequency is very huge. And this magnetic field strength, remember, is nearly 6 lakh times stronger than that of the Earth's magnetic field. Earth's magnetic field is only 50 microtesla, and this is 28.2 Tesla. That is 28.2 into what is called 10,000 Tesla, 10,000 Gauss. This is the Gauss. If you calculate this thing, it is going to be huge value. Okay. So, now let us see what will happen. We understood radio in the NMR spectrum, NMR resonating frequency is in the radio frequency region. We know we calculated the resonating frequency in a given frequency for a given magnetic field for both proton and carbon at two different magnetic fields we calculated. Now let us see what is going to happen. If you look at this, I have a magnetic field let us say 4.68 Tesla. Then if I say proton resonates at 200, simply take the ratio of with gamma. If you know what is gamma, I can calculate fluorine comes at 188, carbon comes at 50 and 2H, deuterium comes at 30 and nitrogen comes at 20. These are the different resonating frequencies for different nuclei in a given magnetic field. Now change the magnetic field, what will happen? I will increase it to 9.39 Tesla, then this correspondingly linearly changes because I doubled this. So then you see keeps on changing, 200 become 400 and keeps going like this. And I change it to some other value, I increase it 5 times. So now 200 became 500, this is fluorine 470 and nitrogen became 50. That means we can calculate the resonating frequency in any magnetic field for any nuclei. So different magnetic field, if you have different nuclei, you can study, and as correspondingly the resonating frequencies are different. This is so far about little bit of understanding about resonating frequency and different magnetic field strength, how we calculate the resonating frequency etc. for different nuclei. There is a classical analogy for this which some of the people discuss in some of the chemistry books. What is this classical analogy? Classical analogy is very simple. I take the example of spin half nuclei. As I told you, spin half nuclei have only two possible orientations, plus half and minus half. In the absence of the magnetic field, they are all randomly oriented. You see, there is no preferred orientation at all. They are all randomly oriented. As soon as I put them in a magnetic field, these tiny magnets start aligning like this. You can see some are in the direction of the field and some are in the direction opposite to the field. Some are opposite, some are in the, and this is the magnetic field direction P0. Okay, they line up either parallel or opposite the direction of the magnetic field as soon as they put it in the magnetic field. And then what is going to happen? These two forces are there which are acting on the nuclear spins in the magnetic field. One is the large magnetic field wants to pull it, keep it aligned with that, and the spin angular momentum wants to spin at a restricted orientation. I told you, we can calculate the restricted orientation, direction of quantization we can calculate, angle theta, I told you. That is also fixed angle theta. At the same time, the magnetic field wants to pull it towards it. There are two forces acting. Then what is going to happen? It is like a tug of war. Like a tug of war, there is going to be a torque created. As a consequence, these two forces makes these nuclear spins to precess, to rotate around the magnetic field direction. This is called precession. This means rotation of a rotating object is called precession. Okay? So this starts rotating like this in a magnetic field. Now it looks like a cone which is opening upwards and cone opening downwards. The reason is for spin half nuclei, you have two possible orientation. Nuclear spins which are aligned like this start rotating like this. The nuclear spins aligned like this start rotating like this. As a consequence, it appears like two cones. Okay, this is what is happening. And these two alpha beta components of the magnetic moment will have a particular quantization direction and start processing in the magnetic field because of the torque that is going to be produced due to two possible forces which I explained. And this is called Larmor precession. Remember, this is called Larmor precession. Then the question you may ask me, okay, they are precessing, that is rotating at some speed. What is the precession frequency? What is the speed at which it is rotating? What is the frequency of it? That you can work out. This is related to the magnetic field strength. Or in other words, we calculated the energy separation between two energy states and then we got the resonating frequency. It is exactly the same. Okay? The resonating frequency is the precession frequency and it is a Larmor frequency. It is nothing but resonance frequency. The energy separation between two states, if we calculate, we know what is nu, resonance condition, we calculated nu, and nu is a resonating frequency, which is also called Larmor precessional frequency. So, resonating, if I say Larmor frequency, remember it is nothing but the resonating frequency of the given nuclei in a given magnetic field. That is what it is. Now, you may ask me a question, what is the energy involved in this? See, if you look at this energy, there are in this table, there are so many things which are involved here. There is a frequency, wavelength, radiation, energy here for different type of spectroscopic techniques. But if you see the last column of it, you will see here radio frequency region, energy is very, very small. NMR spectroscopy falls in very, very low energy region, very, very low energy. Compared to look at the gamma X-ray, there are 10 to the power of 4, 10 to the power of 8, here 10 to the power of -7, 10 to the power of -3, several orders of magnitude smaller. So, NMR spectroscopy is really a weak interaction energy, very, very low energy region. Okay. Now, I want to introduce one term called sign of the gamma. Remember I told you about precession frequency, nu gamma is a gyromagnetic ratio for a given nucleus. Now, this gamma has a particular sign. If I calculate if I know the magnetic moment mu, if I know the angular momentum p, if both of them have the same sign, then gamma is positive. If mu and p have opposite signs, gamma is negative. This is what it is. This is the magnetic moment, this is the nuclear spin, this is a magnetic moment. If they have same orientation, same positive sign, same sign, gamma is greater than 0, positive. And now if they are opposite, that is angular momentum is like this, spin angular magnetic moment is like this, they are opposite signs, then gamma is negative. So what? You may ask me a question, okay, gamma is positive, gamma is negative, how does it matter for us? This matters because some nuclei which have a negative magnetic moment like this, some have positive magnetic moment, but those which have a negative magnetic moment precess in the direction opposite to that of the nuclei with positive gamma. For example, if I have a proton is rotating like this clockwise, let us say, which has a positive gamma. Other nuclei like nitrogen 15, cytine, etc., they rotate in the opposite direction because gamma is different. So, the direction of precession is different. Okay, but the resonating frequency remains same. Then you may ask me a question, how does it matter? Its utility comes in many applications. You will, if you know this only, you will understand. For example, I want to do heteronuclear double quantum, which I don't know whether I have time to discuss. We will see at the end. Of the heteronuclear double quantum between proton and nitrogen. One has a positive gamma, other has a negative gamma. They both precess in the opposite direction. So, when the double quantum, instead of adding, it may become it may get subtracted, it may become negative. We will discuss if there is a time later. So, there are consequences of precession of the nuclear spins either in the direction clockwise or in the direction anti-clockwise. So, this is the concept which you have to know. The sign of the gamma and the direction of precession is given like this. If the gamma is greater than 0 like proton and carbon, they are rotating like this in the clockwise. For gamma less negative, they are rotating in the opposite direction. Can you see the nuclear spins rotating both in the opposite directions? Okay. This is clockwise precession, this is anti-clockwise precession. This is the thing we should know. Okay. Now, I will introduce a term called population difference. What is a population difference? See, as I told you, there are more spins aligned in the direction of the field than opposing it. This is because of the Boltzmann population distribution. That is the Boltzmann equation, and this equation is given by this. The ratio of the spin population in beta and alpha state is given by this equation. It is a exponentially decaying function divided by k into t. K is the Boltzmann constant. Okay. Now, if I consider two energy states of spin half nucleus, I have two spins positive and if orientation for spin half state has been plus of or minus of states, there are number of spins like this. There are more spins in this direction than in this direction. That is all we know. This is the anti-parallel orientation, this is a parallel orientation, fine. So, now the advantage is there is more spin here than here. If I take the difference between the nuclear spin, there is a population. If this number of spins in this state and number of spins in this state are exactly equal, then you calculate the difference in spin population, it is 0. You will not see NMR. I will tell you as you go ahead further, there must be population difference to see the signal. Fortunately, Boltzmann population helps us to have more spins in the lower energy state than in the higher energy state. Okay. So, with this we will have to discuss something about sensitivity of NMR, how do we detect sensitivity, how do we detect what is sensitivity for different nuclei, what is the selection rule, how do we induce the resonance. This is a little bit of discussion. So, since the time is up, I am going to stop here. What I discussed today, see, we discussed about resonance condition was discussed, that we knew, and then we worked out what is resonating frequency for different nuclei in a different magnetic field, and we came to know that NMR comes in the radio frequency region, and if we know the resonating frequency, we know how to calculate the magnetic field strength. And for different magnetic field, what is the resonating frequency for different nuclei we worked out. It is simply linearly varies with gamma, that also we understood. So, with all these things we got an idea about what is happening for the nuclear spins in a given magnetic field. Then we calculated the energy separation and then frequency. Same thing, classical analogy, if I say it is nothing but the Larmor frequency. The precession frequency is nothing called a Larmor frequency, which is nothing but the resonating frequency. So, with this idea, and also we discussed something about positive and negative gamma. If the nuclei has a positive gamma, negative gamma, why it is positive, negative, I discussed. One which has a positive gamma, negative gamma, if I have two nuclei, they precess in the opposite direction in a given magnetic field. If one precesses in the clockwise direction, other precesses in the anti-clockwise direction. It is an important term. These are all have consequences later. With this, I am going to stop here. We will discuss something about NMR sensitivity, how do we get the resonance, everything in the next class. So, thank you very much.